Okay, so on a few of our projects, we've been talking about building recommendation systems around large language models like ChatGPT. And I have been playing with one way of doing that using PostgreSQL with the pgvector plugin, which enables you to unlock vector database functionality inside of Postgres. And I like that because I prefer not to add more tools to our tech stack if I can help it, right? So we can use Postgres as our normal Django database, but as you'll see, we can extend Postgres with vector functionality. Let's dive into it. So I have a repository here of my own. I'm calling it AI experiments, but let's go ahead and get started with the bootstrappers. So I have a terminal open here, and I'll put in our cookie cutter command for the bootstrapper. And let's call it vector demonstration. All right, and we're good to go. Oh, I accidentally created it in the migrations folder. Move it up. All right, so now we can open up our Django application. Follows our normal structure. One of the easiest ways that I've found to get started with Postgres is to use Docker with Docker Compose. And the image that you can use is called Ankane pgvector. So I'm going to plop that in here instead of the default Postgres image. And then I'm also going to change the port to 56432 so that it doesn't clash with any other Postgres instances that I have. It'll load from the .env file, that's fine. And we can grab our database name and password from there. I'll go ahead and create my local .env. Oh, it looks like one was created for me by Cookie Cutter, which is great. The volumes help persist the data between runs of the Docker image. So that's all good and fine. We'll use the server and the client if we want to. Yeah, we'll get into the server code now. So, okay. So I'm going to just build in core. On a normal app, you may want to create a new Django application, but I'm going to scroll down here to the bottom of models.py in core. The first thing that I want to do is decide what I'm going to use pgvector for. So I have a data set here that I found on Reddit, and I've discovered 137,000 job descriptions. Some are in languages other than English. It's very nicely structured data. Every job description is structured like this, pretty clean HTML. So I think this was scraped and then cleaned up and then posted to Reddit, which is pretty nice. A lot of this stuff comes from Indeed.com. I don't know what the terms of use are on this data, but we're not using it for anything professional. What I want to do then is define a couple things. So I'll start with a job description class. That suggestion there, by the way, is from ChatGPT. And we can go ahead, I'm going to go ahead and accept what it's telling me here. I do like the idea of having the title and the description. Those are two of the fields that we get in our data set. So we have title, company, location, a link, which we don't necessarily need, but we could store description and skills. So I'm going to grab all of these. The company can be a care field, can also be a character field. Link I don't care about, description we have, and then skills. This actually is listed out in a sort of JSON or even Pythonic notation. So it's a list of skills. So that's kind of interesting. We can read those. We can read that in and parse it like that. I think for now, I might just save that as a text field to make the import easy. I don't want to order these by title. I'm going to get rid of the meta, and then that string is fine. And actually, there is a field that I want, language. It can also be a character field. This will be helpful to make sure that we're only getting English language job descriptions. And I'll show you how we'll determine the language, because we're not given the language in this data set, but we can use a little AI to detect the language. Let's talk about approach. So we'll start with the job descriptions, and the description field is really the field that contains the most content. So that's the field of interest, right? Okay, so now we have our basic job description model, and we could load this into the database from our data set. And we'll write a loader in a minute. That'll be not very interesting, pretty run-of-the-mill, except for one thing, which is detecting the language. But once we have the job description in the database, then we can get to the interesting part, which is parsing this description into something that we can use for search. And our approach for that will be to use embeddings. Embeddings are long lists of floating point numbers that reflect the location, quote unquote, of the semantic data contained in the description, the location of that in the semantic space. I'm going to define a model here called job description chunk, which is going to store chunks of the description along with the embedding that we generate using the language model. And this can also be an abstract base model. And the chunk itself is going to have a foreign key to the job description. On delete cascade is great. Related name chunks is fine. Then we're going to have a text field for the chunk. GitHub Copilot just generated this for me. I did not write this code previously. Here, now this line doesn't so much make sense. Yeah, I can live with that string. That's probably as good as anything I'd write myself. Chunk type is made up. That's not something that we need, but these two fields are a good starting point. So what we want to add here is not just the chunk content, right, which will be a piece of this description, but we want to also add the embedding. We will be cutting the description up into pieces that are small enough to fit into the embedder. We'll start with this. So what this will allow us to do is feed in or come up with a query, right? So like, let's say we have a student who is interested in acting and has 2 years of experience in community theater, right? We can use this as a starting point, and we can generate embeddings for this one sentence. And then we can compare those embeddings to all the embeddings in the database and find the job description chunks that are closest to this query, and then relate that back to the job descriptions that are related to those chunks and rank those based on the similarity match. So we can basically find job descriptions that are the closest match to our input query, right? And we'll see how to generate those embeddings. It's basically that you set up a model. Actually, that's a good example. We'll be using this sentence transformer in a minute. You set up a model, you set up your query, and then you use the model to encode your query as an embedding. And this will come out as, like I said before, a long list of floating point numbers. And the length of that list depends on the model that you're using. The query embedding would end up looking something like this list, and so on, usually with hundreds of members, if not thousands of members. So that we'll come back to later. But for now, I define embedding as a text field. That's not actually what we want. We actually want to use pgvector. So first, I suppose we should make sure that pgvector is installed. Something I haven't done here is actually activate our pip files. Okay, I paused there momentarily. So now the pipenv is installed. Go into that shell. I'm also going to take note of this path here to the virtual environment so I can set up my Python interpreter correctly in VS Code. I'm going to copy that, paste it. And yeah, it's the full path ending in bin/Python. If I open my shell, it automatically sources the correct interpreter. So now I want to install pgvector so that I can use it with Django here. And so I do python and pip install pgvector. And that installs the Python pgvector package. And again, you have to make sure that the pgvector extension is installed in Postgres and activated. And then you also have to make sure that the pgvector Python package is installed on the Python side so that you can use its features. That's an important detail there. Let's hide the terminal for a second. We're back here to our Django code. We're going to define the embedding. What we want to do is from pgvector, now that it's installed, .django import vector extension. We don't actually need it in the models file, but we'll need this over in a migration file. So we'll create that in a second. And then from pgvector.django import vector field. This is what we actually need in our Python file here. So we'll define a vector field. And then as we define this, we want to set the number of dimensions. So I know already that the model that I want to use has 384 dimensions. So that's the number of floating point values that are in the list for that vector. This is very important. All the vectors that you save and compare have to have the same number of dimensions. And the model that you use, again, influences the number of dimensions that there are. If you use ChatGPT's embeddings, for example, there's something like 1,500 dimensions. This model that we're going to be using actually performs pretty close to ChatGPT and stores its output in fewer dimensions, which is actually a pretty good thing in terms of performance. We want to create a new migration. I think we can just create this from scratch. New file 0002 pgvector or enable pgvector.py. And I copied the initial migration just so we have the template for this. And we'll get rid of all these things. So we're down to operations. It will depend on the initial migration here. We'll do core and then type 0001 initial, just so that it keeps things in order. And then this is not our initial migration, so we'll remove that. We can remove these dead dependencies up here. And now we can move over this import statement. And finally, the one operation that we'll do is to run vector extension. So that'll make sure that the vector extension is set up. Now, we still are using the pgvector image over here, which should have it enabled by default, but it never hurts to make sure that your migration is set up so that, if someone else tries to run this on a database that doesn't support pgvector, it will throw an error. That's our migration taken care of. You can remove this import here and fold some things down just to get it out of our way. Okay, let's just review what we have so far. We have our job description class that has all of the data about our job descriptions that matches what we have in our data set, our dummy data set. This is active thing is here. We can turn that off. And then we have our job description chunk, which will represent chunks of each job description and embed those as vectors in the database for later querying. Okay, the next thing that we have to do, go into our Django app and we'll go into the server folder and we'll make migrations for our new models. So that ran without a hitch. And then the other thing that we want to do is get our database up and running so that we can actually run these migrations and start storing data. I'm going to go ahead and comment out most of the Docker Compose file. So we're only going to be using the Postgres service and not running the server because I want to run the server from the command line so I can get a shell on it more easily. So that's the main reason for that. Docker Compose up D. All right, so now it has started our vector demonstration Postgres database here, and then we'll try to connect to that. So we'll prepare the command. We'll do PSQL, the PostgreSQL protocol. This is the name of our database user, that database user's password, the host, and then the port, and then finally the database name. We need to consult our auto-generated .env file, and we see the user is vector demonstration. So we're going to plug that in here. We see that the password is this big long password. So we'll plug that in here. That will be at localhost, and then it was 56432 that we used. And then finally the database name, which is vector demonstration DB. All right, so this will test that we can actually connect to that Docker instance. And it's upset because of the way that this password is set up. So what I'm going to do is simplify this password just so that we don't have to worry about this here. And now we can get rid of the crazy password in here. We'll go into vector demonstration. We'll do sudo docker compose down, remove this database. Cool. And then we will do sudo docker compose up and then a -d to start it in the background. Copy paste this guy in here. And again, this is after running docker compose up -d. I now have a database. I shouldn't see anything in this database. If we describe the tables, there are no relations, and that's fine. We don't expect there to be any. So we're going to go into our server folder, manage.py, migrate, and this should connect to our Docker instance. It did not. Well, I think it did not because we didn't set the port in our environment variables or in our settings.py. So I think when we come down here, we have db host. We don't have a port configuration on that. So I think by default, it's going to be looking at 5432. So it seems our bootstrapper doesn't account for this, but I think we'll have to add a port configuration here. So let's go ahead and do that. Yeah, the default is 5432, which makes sense because we're using PostgreSQL. And then over in our .env file, we'll add a port. This is not correct. That looks good. And then we'll need to make sure that we force quit, restart our shell to load those new environment variables. Now, if we run migrate, the migrations run. Okay. So now if we open a new little terminal here and run and connect to the database directly, we should see our tables, and we do see our tables. And among those tables, we have the job description and job description chunk. So we can describe job description, core job description. And we see the fields that we created. Those all look correct and fine. And then we can describe the core job description chunk model that we created, and we see the embedding with the vector field. And so this means that pgvector is working as expected, which is great. So we'll close that down. So now on to the fun part. That was all just getting us set up to store these embeddings and job descriptions in the database in the first place, right? So next we want to load in our job descriptions from a file. And I already wrote this up. Because this is kind of trivial, I'm going to go ahead and rush through this just a little bit, but I have for myself another directory where I wrote some functionality for loading in the job descriptions. Now I was using scopg, that's how I pronounce this, the PostgreSQL Python library. I was using this directly and not going through Django's ORM. So there's some raw SQL in here that we can circumvent, but the idea is still basically the same. We will connect to our database, of course. Django does that for us. We will look at the data jobs folder, which I have over here, and find all these CSVs in that directory. That directory only contains CSVs. And then this is called a generator function. We will open each CSV and return it as a file that we can then read. And then each line of that file is a separate job description. So this load all job descriptions calling function calls get job CSV. It goes file by file, row by row, and loads each job description into the database. Let's port this over to Django really quickly. I like putting things like this on the model itself. We could make this, let's say, a class method, and we'll call it import job descriptions. That looks good. Don't need that second parameter. Okay. And then we will bring over our helper function here, get job CSV. Now this is written with a relative path, data jobs. If that's incorrect, then this will fail. So something Django does give us is the setting base directory, base dir. This is in settings.py. This tells you the path to your project. So base directory should be in the same place as settings.py. So from there, we would go up 1, 2, and then descend down into data jobs. So we could probably use that. We're already importing settings over here. So let's do that. Settings.base directory. And then it's always a good idea to import OS in Python and use that to join your paths. Data directory equals os.path.join. Base directory up, 3 directories. There's probably a better way to do this, but we'll stick with that. So then we have the data directory, and then we can define the glob string, glob, the data directory star CSV. Glob, by the way, is a Python standard library that we can import, glob like that. And it too is a generator function. When we call glob.glob, we get back something that we can iterate over that gives us each match for our glob pattern in that directory. Then we iterate over that. We call open on the file, and then we yield that file. This yield statement is what makes this function a generator. So we can also iterate over this function. And so now we can take our loading functionality that I already wrote, and we can do for CSV file in get job CSV, fix our indentation here. And then I have some nice print statements that tell you what's going on. We need to import time. I'm keeping track of how long these imports take. So we're importing time here. We're importing CSV so that we can read the CSVs. And then this, by the way, also is a generator function that you can iterate over. And it gives you the CSV contents row by row. What I was doing here before was setting up a list to receive all the data from each CSV file, and then bulk inserting the contents of that into the database. I'm just going to reset this, so to speak, and then write it from scratch for Django. One thing I didn't delete here is this line, for row in CSV reader, try to detect the language in the description. If there's an exception, set the language equal to blank. This is pretty key for knowing which language our job description is written in. That way we can filter down on only English job descriptions later. I found that this data set has French and Japanese and other languages mixed in, which I'm not interested in. And I think also probably mess with the embeddings because I don't think I'm using a model that is multilingual like that. So I just want to stick with English language and English embeddings. so I need to bring that in as well. So Python im pip install, I think it's lang detect. And this is a Google library. It runs completely offline. It is a little bit slow. It's going to slow down this whole import job. So we could potentially throw an option on here to detect the language in flight, or add language detection after we import the basic jobs. Okay, so we want to detect the language. And the way that we do that is by importing detect from lang detect. And then I'm also importing this exception so that we can catch any languages that can't be identified and just set those fields to blank. And that also reminds me that language here needs to be blank equals true. And we can update our migrations. Great. So now we need to save the instance to the database. So we'll do class.objects.create. Actually, you know what we can do is this job descriptions. We can create a list, and then we can append instances of the class to that list. And then we can bulk create at the end, just like that. So ChatGPT is suggesting that for me. Okay, so here, I'm surprised Copilot isn't smart enough to know what to do here. So we'll do title equals, there we go, row title. Oh, and by the way, I'm using a dictionary reader so that the key names in here will match the row headers in our data set: title, company, location, link, description, skills. So that makes this really easy to write and to read. Not for the AI, however, would seem. There we go. Company. Is it going to pick up on this? Location, description. That's the key piece there. Skills. We'll just bring in the string. And then language, we're detecting here and setting to this variable language. After this block of code here finishes executing, we'll have a list of job description class instances. And when you have a list of model instances like that, you can call bulk create on them, and that creates all of those instances in one database transaction, which is far faster and more efficient than calling .create on each of these as we go through the loop. I also like the idea of separating logic like this from input-output operations, but that's a different story. This should work now. If we go over here to our terminal, shell plus, terminal is all kinds of messed up. There we go. We can now do job description dot import job description. So we can call it directly on our class because this is a class method. And it should be entirely self-contained because it's looking up the CSVs itself and doing all the iteration within this method. So that should be good to go. That seems to have failed because we didn't get any output and it ran way faster than it should have. So that implies to me that it failed to find this directory. So let's do a little testing here. Oh, okay. We actually didn't need to go up so many directories. I think we only need to go up 2. Previous. Okay, so now we're getting a list of all of the CSV paths. And so let's just make sure that we reflect that over here. So we needed to go up 2 directories and then down into the data path. Again, there's probably a better way to specify that path, but I don't want to think about it too much. Okay, so we'll come back in here, job description dot import job descriptions, and we'll let this run. This is going to take a little while, so I'll probably pause the video until it finishes, but we'll watch it for a couple seconds just for the sake of seeing how this works. What this is doing right now, the reason it's thinking so long on the first CSV file is probably because of the language detection. This would go a lot faster without that language detection. In fact, let's just remove language for a minute and do job description dot import job descriptions. Now we see, yeah, it's about half a second to import each CSV. Actually, this is probably a better way to do it. We can get these job descriptions imported and then start embedding and chunking them while we wait for the detector to also detect the languages and save that to the database. So we could also write another class method called detect languages. And here, I don't want to get all job descriptions from the database in one go like this. That'll be a major hit to memory. I mean, we could probably do this locally, would never want to do this in production or on a small machine. I probably have plenty of memory on my current computer, but a better way to do this would be to write another generator function So we could do get jobs, and then we page through this. So we do, let's say, page size 1,000. We could do 1,000 job descriptions at a time. That shouldn't be too crazy. We could start with page size 1,000, and then we want to know what's the count. So what's the total number of pages? So we would do, there we go. Yep, class.objects.count divided by page size plus 1. I see. Okay, so yeah, this will round down to the nearest integer. So we're doing we're doing that plus 1. So order of operations, this will run first, and then it will add 1, and the double divisor will round down. So yeah, that's cool. So that looks good for the number of pages. Yeah, I mean, this is a good suggestion from Copilot here. So we'll do 4-page in range number of pages, and then this is fine because the slicing syntax here in this part of the code actually adds a limit clause to the SQL. So this actually will work fine for our purposes. Okay, so we have the generator there, and we'll go for each job description and get job, okay, let's call it descriptions. Now we'll try to detect the language, update the job description, and then save. Let's test that. Job description dot detect languages. Yes. Okay, so what we want to do is have this be the query set, and then we want to get each object in that query set. So anyway, what this code is doing here is it's getting 1,000 job descriptions at a time. So it's not slamming the database with repeated fetch one queries. And then once it has the 1,000 job descriptions, then it's spitting out each of those job descriptions one at a time using the generator syntax here. So let's go over here. Okay, so let's do job description dot detect languages. I didn't put any update on here, which may be annoying because then we won't know how long it's likely going to take. Quickly add a print statement here. Detecting language for job description. Yeah, we could do some kind of almost like a progress bar. So total JDs, count. We'll increment this with each step of the counter. So count plus 1, JD number count of total JDs. Okay, so that'll give us something a little bit more descriptive to work with. And then we can do job description dot detect languages. There we go. 137,000 job descriptions. And you can see the language detection is actually moving pretty quickly. So yeah, we'll let that continue to run while we move forward to the next step. Great. So now we've already imported all of our job descriptions. We're generating the languages for them and saving that down in a separate function over here. Let's move on to the logic of chunking and generating the embeds. I think I'll add another method to the job description, and let's call it generate embeddings. We can do this a couple different ways. We can throw everything into one big function, so we're generating embeddings for all of the job descriptions at once, or we could write this to generate embeddings for one job description at a time. I think for demonstration purposes, I will do just one job description at a time. Let's actually make this a normal method. So it's going to operate on itself. And yes, so this is a good opportunity to talk about how we're going to be generating the embeddings. So I have a demonstration over here in an IPython notebook. And the simplest approach that I found is to use the sentence transformer library, or sentence transformers library, and the sentence transformer class out of that library. I'm also bringing in auto tokenizer for a different purpose, but this is all you need to generate embeddings locally and offline. We could also use ChatGPT. That would be faster in terms of how quickly ChatGPT can generate embeddings, but slower in terms of the latency of making those API calls, and we may hit rate limits and things like that, or it may be flaky. So I like the idea of generating these embeddings offline. And so to do that, I'm using this all mini LM L6 v2, which has been benchmarked as having pretty high quality and being relatively small. So this is a 400 megabyte model. I think that model gets automatically downloaded when we first initiate this sentence transformer. So that is one piece of this code that is not going to be production ready necessarily, is storing the model alongside of our code. We don't want to download this model every time we instantiate our code and generate the embeddings. But at the same time, we usually won't be generating embeddings on the fly or online. We'll be generating embeddings offline. And once you have an embedding, it stays the same forever. So we don't necessarily need to install the sentence transformer model on every run of the code. But that's all you need to get started. Once you have the model, I think I typed this out earlier, but you can call model encode to embed a chunk. So again, you don't want to be calling model encode. In our use case, we don't want to be calling model encode on an entire job description. We need to split the job description up into smaller chunks first. Then we'll be generating embeddings for each chunk and storing each chunk in the database with a foreign key pointing back at the job description that it came from. We'll also store the chunk so that we can reference it and get a sense of what the language model is thinking when it says that certain things are similar to each other. I'll go ahead and add the transformer import. Now we haven't installed this yet, so we can go ahead and do that. And it's just the Python or PyPy module sentence-transform. Meanwhile, we're detecting languages over there. We'll let that run. I'm going to go get some coffee. Okay, our pip env install finished there. So now we can do pip env install sentence transformers. Actually, I think it would have already installed because I put it in the pip file. So I think we're good now on that front. So let's open a new terminal here. Yeah, let's try it. Okay, so sentence transformer. In fact, we can just try this from the command line real quick. And can instantiate our model, copy, paste. There we go. And now let's encode something. So let's come up with a sentence. This is a sentence about me. All right. It doesn't really matter what the sentence is as long as it's English and as long as it is under the token limit, which for this model is 512 tokens. So I find that around 400 characters or 200 or so words is a good length for this particular model. So we can encode that sentence. So this gives us back a list of numbers that represents this model's understanding of where this particular sentence fits in its semantic space. And we can compare different sentences this way. So we can say, here, let's come up with a new sentence. So, or a query, let's say, what is the capital of France? All right, that can be our query. And then let's define a couple of possible responses, right? We could say the capital of, there we go, France is Paris. And then we can say, now facts don't necessarily matter here, to be clear, but what does matter is the semantics of it. So even if we put in an incorrect fact, if we said the capital of France is Brussels, that actually probably would push this sentence further away semantically from our query, the capital of France. But the LLM wouldn't know the factual difference between those things. It would just know that one is a better match than the other and not necessarily why, right? And that's what makes LLMs maybe not fully conscious because they don't understand those conceptual differences. They're only looking at word frequencies and word likelihoods. But here we can say the capital of the United States is Washington, D.C. All right. So now we have these two sentences that we can compare with our query. So how would we do that? Well, we'd get embeddings for all three of them, right? So we'd get the query embedding, model.encode query, and then we would get the sentence embeddings, model.encode S for S in sentences. And then we would use some sort of similarity metric to compare these. Okay, looking at the docs, I found a way to do this. So we'll need to import the util library from sentence transformer. Util has a function called cosine similarity, COSSIM. And now we can compare our query with, let's say, the first, or our query embedding rather. Yes, query embedding with our first sentence embedding. And we get back this tensor object. It contains a value, and that the value is what is of interest here, with a number between 0 and 1. And the closer this is to 1, the more similar these things are. So we see that what is the capital of France is fairly similar to the capital of France is Paris. So that seems like a likely answer. And then if we compare that to our second sentence, we see that we get a much lower result, meaning this is less similar. And so here, the first sentence is a better fit for our query, but it's more similar to our query than the second sentence. And we could come up with a third sentence, right? So let's do sentences.append. My cat's name is Hobbs. And then we will regenerate our embeddings. And then let's do cosine similarity index 2, which is the new sentence, my cat's name is Hobbs. And we see that's not similar at all. It's even further away. At least here we were talking about capitals. Now we're talking about cats and the names of cats. So hopefully you can start to see how this is useful for storing chunks of a job description or pieces of any sort of document in embedding format, and then retrieving those pieces of documents based on some query and the similarity of that chunk to the input query, right? So that's what we're interested in here. So the way that we will query our job descriptions database is by providing some information about the student or what the student is interested in, then querying for chunks of job descriptions to see if we find matching chunks that match the interests of the student. And then we'll use the rankings of those chunks from the bigger job descriptions to rank the job descriptions in order of relevance based on, we'll also use the cosine similarity metric, but we could also use other distance metrics that are provided by pgvector. Okay, so let's go ahead and do that. We need to generate our embeddings. I'm going to generate this for a couple of job descriptions. This part takes a long time, and it depends on the GPU of your local machine or your cloud resource. So I would recommend doing this offline. Depending on the size of your data set, it could make sense to send this off to ChatGPT for processing, or it could make sense to buy some cloud GPU time and parallelize this process. For now, we'll just run it on my machine. I ran it yesterday, and it took about 90 minutes to generate embeddings for all of the job descriptions, but that includes the ones that aren't English, so we can trim that down a little bit. And we also don't need to import the full data set to get a demo going here. So I'll just do what I have time for, maybe let the embedding system run and come back later. To generate embeddings for a single job description, the procedure will be to first chunk the job description into sentences. This is actually more nuanced than one might think, especially considering the structure of the data that we're working with. Let's take a look at this again real quick. We see that the data is in HTML format. So what do we do about these tags? We'll need to make a decision there. And then we also see that we don't have very clear markers about where sentences begin and end. And there are a lot of situations where we're dealing with lists. Yeah, here's a good example of, here's an unordered list of bullet points. So are each of these, should we consider each of these a sentence, or do we want to kind of consider the relationship between elements in a list and maybe have some of these elements of the list grouped together because these all kind of fall underneath work perks, right? So let's say that a student is really interested in a workplace that has good benefits or good work perks. We may want to consider the work perks as a whole and not break this down into too small of chunks, right? Then again, maybe we could have each work perk be a separate chunk and embed that, and then we'd end up with more matches with chunks on the other end, and we could use that to sort of weight the recommendations somehow. The only way to know which approach is better is to try them and pit them against each other and see which results we prefer. And I won't go that deep in this demonstration. I'll just show you how to get to the point where you could start to experiment and iterate with that. So the way that I was doing this is by simply using another generator. I find generators very useful for this particular exercise here. So I'll just bring this code over and then we can work on it. Okay, so first we'll start with the content of the job description. So that's going to be self.description, right? And then we will want to start chunking our job description. So we'll write a generator here called getChunks. Actually, let me bring over the code I had for that. And as you can see here, I say this is naive chunking of job descriptions. And we set a chunk size, which by default I found 750 to be a good size. So that's 750 characters, not words, importantly there. And then I had another function here, strip HTML tags. In order to keep our inputs to the embedder as lean as possible, I'm removing all of the HTML noise around the words. We really only want and need the English words. Now that HTML structure may actually provide information that could be useful to the embedder. All of these large language models are trained not just on English, but code and things like that. It's possible we're losing some structural information that the system could use to make sort of inferences as it's doing the querying, but we'd have to try that to find out if that's the case. And I'm not convinced that it is, or I'm not convinced that we're losing enough to make it worth it to have to cut down the job description into so many little chunks. It would definitely increase the computation time for generating these embeddings in the first place. And then the other thing is, with all those HTML tags in the mix, a big portion of our chunks would end up being HTML and not actually text. And we're going to be using English text to query the system. We're not going to be using HTML to query the system necessarily. So the HTML doesn't, in my opinion, seem to add very much information to our data set, and it only detracts because it consumes tokens and resources. So I'm stripping those out. That's the long and short of it there. And in order to do that, I need to import the regex library and the HTML library. So I'm going to do that here. Great. And those, again, are part of the standard library. So we have our strip HTML tags helper. We have this get chunks helper, which will take in some content and chunk it into 750 character bits. Again, I'm saying this is naive because 750 characters may not be, it may still be too much. This may end up giving us too many tokens. It also may end up giving us too few tokens. So the variance in the number of tokens that will eventually be embedded will be wide. We may also have some blank space that we're encoding with this, and I'm not going out of my way to make sure that we strip that white space. But I am removing new lines and replacing that with a space because we don't really need the new line content. Again, this could go either way. Maybe the new lines are important information, but again, we'll be querying with simple paragraphs, sentences and paragraphs of text that won't have new lines. And so I don't know that there'll be much informational benefit in retaining the new lines. Oh, and by the way, all of our job descriptions now have languages attached to them, it seems. Yep, just finished over there, so that's great. And we can count real quick the number of job descriptions that are in English. So there's 74,787 job descriptions in English out of a data set of 137,000. So there are quite a few job descriptions in this data set that were not in English. And so this should also reduce our embeddings computations. And then, yes, so while we continue to have content, we're going to grab a chunk. So we'll slice the front of the content to get our chunk, and we're taking the first 750 characters out of the content. And then we are updating the value of content with everything else. So content is getting shorter and shorter. That's why this while loop will eventually end. Content gets shorter and shorter, and it spits out one chunk at a time, which we can do work on. Okay, so then down here, we're getting the JD content. So we can do get chunks, and we can save ourselves some lines of code here. And something else, okay, so this is what's called a generator expression. It's sort of like a list expression, but instead of using square brackets, we use parentheses. And so this gives us a generator function that we can then iterate later on. We'll do that down here. But to walk through this really quick, what we're doing is for each chunk, so for C in get chunks, for each chunk of the description, we are getting the chunk content, that's C. We are then tokenizing the chunk content. So we're turning the content into individual tokens. The reason we want to get those individual tokens is because I want to keep a count of the number of tokens that we have. We're not actually going to use this. I'm just keeping track of the token count. And in fact, that reminds me that I wanted to add that here. So token count integer field. Yeah. Let it be nullable. Okay. All right. For the tokenizer, this is where I was using Transformers Auto Tokenizer. Transformers is, I believe, installed as part of installing sentence transformers. And then we get the embeddings. So I'll need to, well, actually get chunk embedding is simply calling our model.encode. So really we just need to set our model up. So that's really step one, set up the embedding model. Step two, chunk the job description into sentences. And then step three, save the embeddings for each chunk. So we'll come back to that. So model will be, I thought I had already brought this in. Sentence transformer. Nope, just the import. Okay, so model will be this model we defined before. Okay, and then instead of doing this, we can do model.encode. And then we'll also need to set up this tokenizer. So the tokenizer will be auto tokenizer from pre-trained all mini LM L6 v2. Yeah, let's actually preview what this looks like. So we can import auto tokenizer, copy paste this over here. It isn't happy. Oh, I remember. For this to work, we need to prefix it with sentence transformers. So it's part of the transformer library, but it's sort of a dependency. Whereas here, because we're using the sentence transformers library, this model is built in at the top level, but it's not built in at the top level of this other library, sentence dash transformers. There we go. Okay. So now we can preview what it would look like to tokenize a sentence. So this is my sentence. It contains a cheeseburger. And you see that it breaks the sentence down into what it considers logical tokens. And the reason I added cheeseburger in there is because I know that that is a word that contains multiple tokens. Cheese, burg, and And the period, you'll also see that the punctuation there is identified as a separate token as well. So when these LLMs work, like ChatGPT, what they're doing is they're taking in a string of tokens like this, and then they're predicting the next most likely token. Not the next most likely word necessarily, but the next most likely token. So that could be a bit of punctuation, that could be a symbol, that could be a piece of a word. And that's also how GPT can make words up, because it can combine different pieces of words if that makes sense in terms of its statistical predictions. So that's pretty cool. Okay, here's a good example, therefore, of how the number of words does not reflect the number of tokens. There are 11 tokens in a sentence that has 1, 2, 3, 4, 5, 6, 7, 8 words. Okay, so that's a good example of what the tokenizer is doing. So here I'm just tokenizing each chunk of content, and then later plan to save the length of the tokenized content. Okay, so now we want to save the embeddings. So we're going to call our generator expression and iterate over it. So that's what we're doing here. And we're then expanding we defined a tuple in here, right? So we're expanding that tuple into variables, chunk content, chunk tokens, and chunk embeddings. And then we're appending that to the data. So we have self.id as the job description's ID. And then I'm going to do what I did before, which is to create a job description. No, in this case, we're creating a job description chunk instance for each iteration. And then, and then we will bulk create those at the end. So we'll call these JD chunks. And then we're going to do that. Yep, bulk create. This is running for one job description. We are setting up our models, which maybe could happen outside of this function if we wanted it to. These could be globals. But we're setting up our models. Then we're getting the chunks of the description. So this generator here is what actually does the chunking. And then for each chunk, we are tokenizing and encoding that chunk. And then we are instantiating a job description chunk model. I'm saying chunk an awful lot. It's getting funny. We're instantiating a job description chunk for each chunk. And then keeping track of the content in each chunk, the number of tokens, and the embedding that we generated from our model, and bulk creating that here. So this should be a complete implementation. Let's see if we made any mistakes and if this works. Go back into the shell, and we'll get a job description. Let's just get the first one. and we will generate the embeddings. You know what? We need to define these as keyword arguments, of course. So this is going to be the job description. And in fact, I think this, we can just pass it self here. And then the chunk will be the chunk content. Token count will be this. And the embedding will be chunk embedding. Let's restart our shell here. Get the first job description. And then do jd.generate embeddings. All right, let it run. Okay, that was pretty quick. So now we can do jd.chunks.all to see the related chunks. Aha, well, this is where relying too much on the ChatGPT can get you in trouble. But it put a made up attribute into our string. Actually, it had added that as a field before, and I didn't catch that it also added it to our dunder string method there. jd job description.objects.first, and then jd.chunks.all. And we see the chunks there. Let's see how many chunks we have. We have 6. Okay. And so now we can go through and look at the content if we wanted to. Chunk in jd.chunks.all. Chunk. So now we see how this, let's actually print a couple new lines between each one so it's easier to see. There we go. So these are the individual chunks out of the job description. We see some clutter at the top here, actually, some CSS that got mixed in with the HTML. So it might be good to actually strip out that CSS if we can, because we see how now the content is the content of this chunk is kind of squished into the end. So this chunk is not going to be very useful to us. We see another potential issue here in that we're cutting chunks up by the number of characters and not cutting cleanly at the edge of words. So that could be an improvement that we make. Again, tokens can correspond to pieces of words. And I found that ChatGPT, for example, is pretty good at picking up on misspellings and partial words, but could be improved, I think. And also, like I was saying before, just finding better logical separators in the job descriptions that are reliable could be a good idea, whether it's separating on periods or actually reading some of that HTML structure and chunking based on the list content, or even asking ChatGPT or an LLM to extract information and put it into a structured format, such as extracting the salary and determining whether the salary is high or low for a particular job. You could get really intricate with how you do your chunking and your analysis of the data set. So, I glossed over that part here and did this in a very basic way. But I think that, garbage in, garbage out, as they say, and finessing your content will potentially improve the quality of the recommendations that you're getting out of it and the sensibility of the recommendations that you're getting out. But I wanted us to get to a point where we had some data we could actually query, and that would be interesting. So, the other thing we can look at here for each chunk is the embedding here. So we do have a chunk, and we can look at the embedding for that chunk. And again, not much to see here, but we do see that we're storing, 384 values. And now we can start to do some interesting things with this, like query against it. So how would I run a query? Well, first of all, let's generate more embeddings from our job descriptions. So let's say 300 job descriptions, and let this run real quick. So for JD in job description.objects.filter language English, and then let's limit this to 300. I think that's all we want to do there. JD.generate embeddings. All right, so we'll let this go. I want some sort of progress indicator. Print. Yeah, let's do count equals 0. Count plus equals 1. Print generating embeddings for JD number count. For JD number count, JD.generate embeddings. right, let that go. Okay, that finished generating embeddings for 300 job descriptions, which is great. But it occurred to me that it's probably starting at the beginning or maybe iterating through these in the order that they were imported, meaning that most of these job descriptions are probably accountants, which is not very interesting for our purposes. That did take about 2 minutes to run. And so you can imagine for 75,000 job descriptions, it's going to take quite a while to generate the embeddings, maybe an hour or so. What I'm going to do is change the order by statement here to order by random job descriptions. Okay, so I'm going to do this. I'm going to reset this job description chunk.all.delete. I guess that changed. We'll just delete all of the embeddings we've generated so far. And then we will, this time around, order by question mark, which should give us random results, a random sampling throughout the entire database. I'm going to go ahead and bump this up to 1,000 jobs, just because I think that'll be more interesting to look at. Let's do that and let that run. Oh boy. Nope. That's not what we wanted. Okay. Let's reset the counter. Count plus equals 1. Go. Put the print line in there and generate embeddings. I think that's all we need. All right, let that go. So we're about halfway done generating the embeddings. I'm going to let that run on the side. I figured we could go ahead and get started on the querying side of this. Just a refresher, what we're going to start with is something like what a student is interested in. So we can say the student would prefer a job in the arts. They have a background in finance, or let's not complicate this. Let's make this very straightforward. They have a background in choir and theater. Yeah, that's a fine recommendation. Well, let's start there. I mean, we could add more detail, like their major. We could say their major was, yeah, sure, music, minored in theater, graduating year 2022, something like that. And we could provide as much detail as we like, as long, again, as it fits within our token limit. So we're going to start with a query like this. And then what we want to get back is a list of, let's say, expected result. Expected result is a list of job descriptions in descending order of relevance. So just like the content preparation side, the querying and search side of this also has a lot of nuance. I'm going to show a very basic way to do this. It's not necessarily the most performant way to do it, but it gets us some results that we can start to look at very quickly. So let's just write a search function. So search, we can just call it search, and we can put it up here as another class method. How about that? And we'll move this up here. And meanwhile, our embeddings have finished. We're going to be searching against chunks. And so I don't, I put the search method here in job description because I think, that's where we've been putting all the methods. So it's kind of sensible, but just a reminder that we'll be searching against the chunks, not the job descriptions directly. .objects. So in order to query against our embeddings, we need to bring in a distance algorithm from the pgvector Django library. So we'll bring in L2 distance. This is a bit different from cosine similarity. We can also bring in, actually we could bring in cosine distance. Maybe it'd be fun to compare those two and see what we get. So it's similar to querying on a normal field, but because we are doing comparisons using the distance function, distance is not a literal field on the object, right? So we need to annotate our query set with the distance of interest. So let's use the L2 distance. So when we use L2 distance, we use it in a similar way to other model functions like the Q function or the F function. We wrap the field name, that's embedding, so that needs to match our field name on the job description chunk model. And then we're going to supply it with a query vector, which will be the, for now we can use what we defined up here and then vectorize it. So we'll need to bring our model in, same way that we did here, define our model, and then query embedding. Let's call it an embedding because that's what we call it everywhere else. Model.encode query. And then we can do query embedding here. There we go. So now when we get back, first of all, this is going to query all of the job description chunks. Okay, so this will grab all of the chunks and then annotate them with the distance to the query embedding. So let's start there. We can put the search term here. Then we can say query equals query, or the default one we've kind of programmed in there. And then let's just return our annotated query set. So if we bring this into the shell now, we do job description dot search. This will take a moment because it's comparing with everything. Has no attribute default alias. I think it means we are supposed to give L2 distance an alias here. Maybe something like this. Well, yes, the manager doesn't have it because it's a class method. There we go. Okay, there we go. Or let's call it JD chunk results. Cool. And then the length of that should be, that's all of the chunks in the database, right? So let's get the first one. Dot first should work. Yep, because it's a query set. And then here we can check out the distance because we set that as an alias. No, we cannot. Maybe we need to annotate it instead of aliasing it. Okay, so we'll do job description dot search. And after a time, we'll get back some results. There we get our results back. And then we'll do, let's call it JD chunk results, job description dot search. We'll just search again. Let's look at the first result. Let's see if we can inspect its distance from our query. There it is. So the distance comes in, and again, this is L2 distance, in this case, not cosine distance. The distance is coming in at 1.3. Do we know if that's good or bad? No. The only way we could know is if we sort our results. So let's go ahead and do that. Results.order by. And again, we can do this because we're working on a query set that's annotated by distance. That's what our search method already did for us. Okay, so that works. And then we can do for chunk in JD chunks. Let's just get the top 20. Chunk.distance. And let's go ahead and do chunk.jobdescription.title. So we can see the titles that are being recommended to this person. So remember, this person would prefer a job in the arts. They have a background in choir and theater. They majored in music. They minored in theater. And then we threw in the graduating year just to see what that would come up with. And we get back results. We're ordering from the lowest distance to the highest distance. So because this is a distance algorithm, low is good. That means it's a close match. If we were to flip this and do the descending ordering, we would find longer distances here, and in theory, less relevant results. And at a glance, this, UX researcher, that's kind of a creative field maybe, but we get data analyst, deal entry business analyst, strategic sourcing, those, and senior finance. Those don't look like artistic jobs necessarily. So I have a good sense that that this is working. Okay, so we notice that what we've ended up with here, though, is not job descriptions, but just chunks of the job description. So what we would like to do is get the top 10, 20, 30, 40 jobs, not by chunk, but by a full, complete job description. So we could try to figure out how to do that with the Django ORM. I was thinking about that, and it seems a little bit complicated. So what I'm going to do instead is sort of coalesce our values in Python here. So the way that I'm going to do that is by All right, so what we're doing here is we're looping over each chunk. If the job description ID is already in the dictionary, then or is not already in the dictionary, then we're going to add that key, the ID, to the dictionary, and the value will be a dictionary that contains the job description object, not the ID, but the object, and then starts a list of chunks by adding the current chunk to the list. Otherwise, if the job description ID is already in our lookup dictionary here, then we can append the current chunk to the existing dictionary. This will allow us to gather everything together like that. Actually, I'm going to go back to calling this results because we ultimately want to return this. Then we can iterate the dictionary. So we can do for kv in results.items, and we're going to update each one with basically with that. So we're updating each dictionary. We're adding a score field, and that's going to be the average of the distance of the chunks. Copilot strikes again and does a great job with it. Now, the results we get back are going to be kind of weird. There'll be this dictionary. Yes, we could do this. We'll go back to unique JDs, but then we'll make results be a list. And we can do results.append the job description. So we can compute this score. Instead of updating the dictionary, turn results here. Instead of updating a dictionary, we'll compute this score. Well, we could do, a less hacky way to do this would be to have results be a list of tuples, just like it's suggesting here. So probably put we can put score first. That way we're not modifying a Django object. So then we'll have the score paired with each job description, just like that. It'll be interesting to see what this does with ordering. We may need to sort the results one last time before returning it. But this should now give us a list of job descriptions with their related score rather than job description chunks. And the chunks have they've kind of been discarded. We could do this, though, to keep the chunks around and make sure that they get returned with the results. So let's see what that looks like. So we'll do results equals job description dot search, and we'll just use our usual search query. This will take a while because it's computing this on all job descriptions. Okay. Again, we may want to pre-filter what we're querying against, or we may want to create an index to optimize the query or only get the nearest neighbors. It is possible to filter by nearest neighbors as part of this distance calculation. I didn't demonstrate that before, but yeah, if we simply add slice on here, we could get the 100 nearest neighbors by distance, and that would be that. Or that would be a lot more performant because then it wouldn't be comparing necessarily against every single job description in the database, all 100,000 of them. But I like this because now we have all of the distance comparisons, so we can rank them in order and see how our recommendation algorithm is performing. So then we can do for R in results. Let's look at it. For R in results, and let's just get the top 25. We can peek at those, and they are tuples. The chunks are making this hard to look at, so let's just do R0, which is the score, and then R1, which should be the job description. We can do that. Just grab the title out of that. There we go. So yeah, we see the results that we saw before, but now these rows each correspond to a specific job description instead of chunks. And the score that we see here is the average of the scores of all the chunks. So it's sort of an aggregated version of what we were looking at before. And we see that these are somewhat out of order now because of the averaging that we did, but somewhat still in order. So we would need to add one more sort to this. So we could probably do it on this. Sorted. I'm going to see if Copilot can help me out here. There we go. Yep. So we'll sort the list of results by their first key, which is the score. And then this would be in ascending order, which is what we want because we're using L2 distance. So let's back out of this, come back in. results equals job description dot search. 4 are in results, and then we'll do R0, R1 dot title. And there we go. Oh, I listed them all out again. All right, let's just do the top 40. There we go. And now these are in order from the best match to the least best match, and that is looking good. So yeah, so that's just a basic walkthrough of how to set up Django models in such a way that you can store vectors using pgvector, and then you can query against those vectors using the distance algorithms provided by the pgvector Django package. In this case, we used L2 distance, but you could also use cosine distance. I think you can use Euclidean distance and import those functions. Whichever you prefer, whichever your experimentation shows, delivers the best results. And this is where the magic really is happening. Things got a little bit messy down here. Bet there's a better, easier way to do this that I'm not thinking about right now. But this part, at least, is all you really need to execute your query to get matching bits of data that you had embedded and stored in your database. So yeah, I hope this has been informative and helps you on your machine learning journey.